Thank you for tuning in to Transparent Physics. This lesson is part of the Physics Toolbox series where we teach you the skills that you're going to need to know in introductory physics to succeed. Today, as you can see, we're going to be talking about QUIPS. QUIPS is a problem-solving strategy. Now, there's a lot of acronyms out there for how you should go about solving problems. This is the one that I've found works. It's little bits and pieces that I pulled from the different ones that I've encountered, both in my education as a physics major and then also in my career as a physics teacher. So I like to consider this the best practices. I invite you to take a look at what I have to say, and if you think some of the stuff I say has merit, incorporate it into what you do. You can always come up with your own acronym, but QUIPS is pretty catchy. So take a moment for a sip of tea here. And let's get started. So, QUIPS. If you had to guess what the Q stands for, not really. I don't know how many words in the English language start with Q, but the one that's most likely to fit in this scenario is the idea of the question. You cannot solve the problem unless you know what the question is asking you. So I encourage you to read your question carefully. Watch for details. One of the challenges in introductory physics is that a lot of the problems are word problems, and we're not used to those from, say, chemistry or biology. So you sort of have to weed through some narrative. You have to maybe disregard some irrelevant information, but take the time to read the problem carefully. Also ask yourself if you've seen a problem like this one before. There's lots of different ways that we can phrase problems in physics, but ultimately at an introductory level, you're seeing from a relatively small set of equations, relatively small set of possible scenarios. So even if it looks different on the surface, you may have already solved this problem before, just with maybe some different measurements. So the Q is for question. Read the question. The U it's a sometimes U, I'll be honest. If you are allowed to write on what you are working on, the U stands for underline. And so if the circumstances permit, underline the information as you encounter it. If you've ever taken some test preparation courses or anything like that, they often recommend the same thing when you're reading your problems in your packet as well. As you encounter information that you think looks important, underline it so that when you come back to it later, it's easier for you to catch what you thought was important. Things that might be important are the information that they give you, unknown values, and sometimes they're going to ask for the answer in terms of specific units. All those things are handy to remember later on in the problem, so while you're reading it to begin with, underline it. If you cannot underline, let's say you are reading a problem out of a textbook and you're not interested in defacing your textbook, or if your teacher tells you not to write in the packet or something, if you are not allowed to underline, then don't worry, the U just becomes part of the word question. So the acronym is still valid. It's the QU for question, and we'll just skip the underline and move on from above. So don't worry, acronym integrity maintained. So you've read the question, you've emphasized the important information, and then the next thing we go for is look at the information that we have. You're interested in organizing what you know. Sometimes there's a lot of information out there, and it's a little hard to tell what's important and what's not, but you want to make sure that you take the time not only to know what's there, but know what its role is. So organize what you know so far. In most cases, in introductory physics, you'll be able to draw a sketch. I'm not talking about an illustration. I'm talking about a real quick, simple, stick figure-y kind of sketch just to get the information down. Most problems in introductory physics lend themselves to a visual interpretation. It helps you understand the problem better so that you're putting the information in the proper places. You're going to be given knowns. When you're given knowns, make sure you include variables and units. The variables are things like D, V, T, A. The units are things like meters, seconds, meters per second, newtons. Make sure you include both variables and units. The variables are important to make sure you are choosing the right equation. The units are important to help make sure the answer works out the way you think it's going to. Also, make sure you list your unknowns. When you are not sure of something, if you don't know the answer to something in physics, try to avoid creating x as the unknown. In most cases, you will be able to assign it to one of your variables. For example, if you don't know what time is, then t is your unknown. It's not x. I know in your math classes, sometimes the x is the default variable for something you don't know. In physics, you're going to have a whole shelf full of variables to choose from. Use the variable that's appropriate for the measurement. Don't use x if you don't have to. Although we will use x for like horizontal motion, but that's a different x. So you've read the question, you've underlined the important information, you have organized your important information, and next up is P for procedure. Basically, you want to plan how you intend to solve the problem. Now, you're going to take a step back, you're going to look at what you know, you're going to look at what you don't, and you're going to think about specifically what equation connects what you know to what you don't. In introductory physics classes, your problem is going to have an answer, and it's probably going to be an equation that you were taught relatively recently in class. So we're not, searching the world over for the answer to the question. It's usually pretty clear once you've identified your initial information. You might have a couple choices in terms of equations. You might just have one. Generally speaking, though, you'll be able to identify an equation or more than one equation, if it's a multiple step problem, that connects what you know to what you don't know. My personal preference in this stage as well is to manipulate the equation for the unknown variable. That means if you have the equation, say d equals vt, and you're trying to solve for v, I have always been of the opinion that you get v by itself, you algebraically manipulate it. And there'll be videos available to talk about algebraic manipulation. It's an extraordinarily important skill in introductory physics. I'm not going to go into the arguments now why I think that's a good idea. I'm just going to plant the seed now. As part of your procedure step, get your equation manipulated so it's all ready to go. So now you've read the question, you've underlined the important information, you've organized your important information, and you've set up a plan for how you solve the problem. All of these together are a majority of the work you're going to do to solve the problem. The last step, the S step, is actually really just turning the crank at this point. You've set everything up ready to go. It's like a set of dominoes. You've got it all set up. You just knock it over, and you are ready to get the answer. So S is finally the solution. So take what you know, plug it into your equations, which you probably already manipulated at this point, and solve it out. Show your work. Even if it's obvious to you, somebody is probably grading this work or taking a look at it. So make sure that somebody else can understand what you're doing as well. When you get the answer, ask yourself if it makes sense. If you're timing the amount of time it takes a rock to drop from a bridge into a river, and you work out that it's like 3.5 hours, it's probably not correct. So the advantage at introductory physics, a lot of times, your problems deal with scenarios that are fairly easy to visualize. Again, you don't always get intuition helping you, but when you can look at a problem and say, you know what, I think this might not make sense. It could just be the problem. It could be a goofy problem, but it's possible that you made a mistake on your end as well. And it's always just a good idea to circle your final answer. That way you make it clear. Save whoever's taking over, look over your work a little bit of time. So these steps together, taken in full, are a great way to get yourself situated for solving all kinds of problems. It is a technique that you can use pretty much all your way through physics. Again, you're going to read your question, you're going to underline the important information, you're going to organize the important information with variables and units, you're going to determine your procedure. The procedure is, again, focused on using the right formula, choosing the right equation and manipulating it, and then you're going to actually solve it out. That's it. Introductory physics is a lot of the same thing. Again, you'll have different initial information, you'll have different formulas. It may feel different when you move to different units, but it's really the same procedure every time once you get the hang of it. And a little quote to wrap things up here. A problem well put is half solved. Honestly, I think John Dewey underestimated it a little bit as far as physics goes. If you have put your problem well, I would say well put involves the first 4 letters. And again, that's more than half solved. That's like 80% plus. So, but hey, point well taken, John Dewey, nonetheless. Hey, I'd appreciate you tuning in for this lesson from Transparent Physics. I hope this tool in the toolbox will serve you well as you look to solve problems as you explore introductory physics. And I hope this has had the opportunity to make physics a little clearer for you with Transparent Physics.